All right. Welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions. Or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Dr. Ballarin, who is an assistant professor of numerical analysis at the Department of Mathematics and Physics, University of Cattolica del Sacro Cuore, Brescia in Italy. He graduated in mathematical engineering at Politec di Milano, defending his bachelor's thesis in 2009 and master's thesis in 2011. He then pursued a PhD in mathematical models and methods in engineering at MOX, the Department of Mathematics and Politec di Milano, defending his PhD thesis in 2015 under the supervision of Professor Alfio Quattroni. After his PhD, he has been postdoctoral research fellow from 2015 to 2018 and assistant professor of the numerical analysis in 2018 and 2021 at CISA Math Lab in the group of Professor Gianluigi Roja. Since March 2021, Francesco is a tenure-track assistant professor of the numerical analysis at the current university. His research focus in particular on reduced order models for parameterized problems in various applications, mainly the computational fluid dynamics. He is author of more than 50 publications on numerical analysis and scientific computing and related topics. He is also a passionate developer of open source software libraries, both in C++ and Python, that become an integral part of his research activity. All right, today, Francesco will talk about regularized reduced order models for control of Navier-Stokes equations. Please enjoy and expect a wonderful talk. But now let me ask one question to Francesco, just to make this seminar somewhat informal. Okay.
Yes.
Our question is you're definitely passionate about the reduced order models. Is there a moment in your life when you realize that, wow, this is it. This is the field I would like to commit my career, at least for now. Is there any moment?
Is there a specific moment? I mean, I guess that I have to thank the fact that since the very beginning of my career, I basically started working on this topic since the very beginning of my career, since my early PhD student days. So is there a moment in which that was sort of decided? Probably, I'm not saying the first day of my PhD, but somewhere in the first year of my PhD. And I was lucky then to continue working on this in strong groups in Italy. So I would say that maybe it's not really a moment, but it's a combination of different moments that have allowed me to, even though I changed different locations, to keep working on this topic.
Interesting. Well, yeah, some people keep their PhD work and keep doing on the same research even after they become a faculty, but a lot of people actually change their topic, right? But you're not that case. Interesting. Well, thank you.
Yeah, I would say probably not changing it, but like adding bits and pieces. I would be open to it. Probably changing it altogether, not yet. Let's say.
Okay, great. All right, stage is yours.
Great. So thank you for the introduction and for the invitation. And yes, so if you heard a few minutes ago about my main research topics, you could probably guess that I will be talking about reduced order modeling. You could probably guess after reading the words computational fluid dynamics that I will be talking about Navier-Stokes equations. And in particular, let's say the two keywords that probably after hearing the introduction you may not have guessed are these regularized and control. And so let me jump into these two keywords, and let me have a first sentence that should somehow guide us throughout the presentation. So the goal of this talk, and really not only this talk, but the two papers that you see at the bottom of the slide, and overall this research topic I'm working on, is to discuss flow control strategies for flows which are, let's say, if not turbulent, mimicking turbulent flows. And the hope would be that this strategy is characterized by an high computational efficiency. And this objective will be reached by means of three main ingredients that I will be discussing throughout the presentation. And I will jump to ingredient number 3 because it's probably the one that we are most used to, and it is reduced order modeling. And in particular, for the sake of this presentation, I will choose one specific reduced order modeling technique that is basically a reduced Bayes method, or a reduced order model based on a Galerkin method. Then for this audience, I will also need to introduce two other ingredients that are, let's say, less specific of the context of this seminar series and reduced order modeling. The first one is feedback control, and I will introduce this as, in my opinion, a practical way to steer the flow of these Navier-Stokes equations, for instance, towards a desired configuration. And the second ingredient is are regularized techniques, as again a practical way to handle flows with larger Reynolds number using spatial filtering. So for each of these three ingredients, I will have a sort of a slide or two, or whatever is needed, that discusses an overview of the methodology. Then, if you noticed, I used this word practical in the first two sentences, so I will discuss what I mean by practical, and I will give you a numerical test case to convince ourselves that this is actually a method that could be working. So throughout the presentation, I will be basing the content of the slides on two references that you see at the bottom of the slides. The first reference, number 1, is co-authored with Maria Strazzullo, Traian Iliescu, and Claudio Canuto. And this will be the reference for part A, which will basically be most of the talk. And then in the final, I don't remember, like 8 slides or so, I will have a second part, part B, that is based on a second work in collaboration with Anna Sanfilippo, Ian Moore, and Traian Iliescu again. And the two parts discuss in particular two different regularization techniques. In both parts, our state equation, so the model, the physical model, will be time-dependent incompressible Navier-Stokes equation. So to set the notation, our goal will be to find the velocity that I will denote with lowercase u, and the pressure that I will denote with lowercase p, such that these time-dependent Navier-Stokes equations are satisfied. So the Navier-Stokes equations are the first two equations in the system, and they are set on a domain omega, which, for the sake of the two different papers I took this material on, is slightly different in the first paper than in the second paper. But in both cases, this corresponds to two well-known test cases. So in the first part of the presentation, the domain omega will represent the well-known benchmark of a flow past a cylinder, while in the second, which is the domain at the top here, while in the second part of the presentation, we will switch to another test case, which is still well known, which is the case of a backward-facing step. So in these configurations, the flow is coming in from an inflow section that is denoted with gamma in, leaves the computational domain through an outflow section gamma out, and may encounter some walls which are denoted with gamma W. So during the introduction, it was mentioned that I mainly work in parameterized problems. So if this was a parameterized problem, the ideal parameter, the typical parameter would be this nu, which represents the viscosity. And to mimic turbulent flows, we will assume that the viscosity nu is small. That is, the Reynolds number is large. Actually, in this case, I will not be considering a parameterization. So nu for us will be fixed, and the parameter that I will be reducing will be the time. So basically, my reduced order model will be built compressing the time dependence of these flow configurations. So for this audience, I should be able to go quickly over these two further slides. So the reduced order model that we use is a Galerkin method built on a reduced basis space. So for us, the data that we will be using to train this reduced order model will come from an high fidelity discretization, which is based on a finite element discretization in space. And this finite element discretization in particular will be based on a Taylor-Wood finite element method. And for the sake of notation, in case I need it elsewhere, the step size will be denoted by the mesh size, let's say it will be denoted with H. And in time, for simplicity, I will give you a time discretization using implicit Euler. And again, in case I need it, the time step size will be denoted by delta t. So again, to set the notations, the discrete velocity that comes out of this full order model will be denoted with lowercase uhn, where n is the index of the current time instance. And so, as usual in this context of reduced order modeling, we will have two phases. During the offline phase, or the training phase, we will be building a reduced order model based on a reduced basis space that we obtain by compressing the temporal evolution, as I was saying. So our parameter will be the time. And out of the compression techniques, we will be choosing a proper orthogonal decomposition method. And after this compression, we will be constructing the reduced basis space of dimension lowercase r, and I will be denoting with capital VR this reduced basis space, and this will be built as the span of the first R periodic modes, phi1, phi2, up to phi r of x. The second phase, the evaluation phase or online phase, is instead a Galerkin method on capital VR, and that is, we assume that the round velocity has the following, as this expansion. So it's a linear combination of the modes, of the POD modes, phi j, multiplied by some time-dependent coefficients, Cj, which are the unknown of the reduced order model. And in setting up a Galerkin method, we plug this expansion into the weak formulation of the original equations. So the goal is to find R time-dependent unknowns, C1 up to CR, such that this formulation holds. And this formulation is, as I've written it here now, is semi-discretized in space, is discretized in space but not in time, but then one can further discretize this in time, for instance, again, by means of the implicit Euler method. So overall, the online phase of the reduced order model can be equivalently rewritten as a dynamical system, which is of small dimension R and is quadratically nonlinear. So for the sake of setting up the notation at the reduced order level, we will just need to introduce three quantities out of a pre-computation. M is the reduced order stiffness matrix, K is the reduced order, no, sorry, M is the reduced order mass matrix, K is the reduced order stiffness matrix, and Q is the third order tensor associated to the nonlinear term. And the good news is that each of these three tensors can be preassembled once and for all at the end of the offline stage. So for those of, if there is among the audience someone who is familiar with these Navier-Stokes equations or these incompressible fluids, they may have noticed already that if I compare the equation at the bottom of slide number 3 with the original Navier-Stokes equation as I brought it in the Strang formulation, you will see that on slide number 3, the pressure unknown has dropped out. So this is possible because the ROM is built on bases which are by construction discretely divergence-free. So basically, the short version of this topic, of this second bullet in slide number 4, is that during the online evaluation, you are not required to solve for the pressure because the divergence constraint is automatically satisfied. So in this setting, for the rest of the presentation, our only unknown whenever we'll be dealing with the reduced order model will be the velocity. But if there are for sure alternative reduced order models which allow to recover the pressure as well. And for instance, one possible option is related to supervisor enrichment or stabilization methods, which somehow are related to a pressure boson formulation. For the sake of this presentation, recovering the pressure is not essential, so I will not do that, and I will only focus on the velocity unknown. So let me now start on this first part, which is about feedback control and an adaptive regularization technique, and in particular, an evolve, filter, relax regularization technique. So I promised you 3 ingredients. So look at the top of the slides, and these slides, title of these slides will, once we go through them, will highlight which ingredient we are currently on. So right now we are at the first one. So the first one was feedback control. So in feedback control, we imagine that we have a target velocity, which is physical, so divergence-free. And I will be calling this target velocity with capital U. So the goal of feedback control is to have, let me say it in words first, is to find a way to steer the actual Navier-Stokes velocity, lowercase u, towards the target one, capital K's, capital U. At least, maybe not at the very beginning, not for very small times, but at least as time increases. In a mathematical sense, what we are asking this control to do is to make sure that if you compute the norm of the difference between the physical velocity and the target one, let's say the L2 norm squared, at the very least, this norm in time, the derivative in time of this norm should be less than or equal to 0. So the norm squared should be decreasing in time. And the rules that we give to this feedback control are that it can only operate on a forcing term, F, which acts on the right-hand side of the momentum equation. So I have now written again the momentum equation, but I have highlighted a term on the right-hand side. This term will be a sort of forcing or a gravity that now can depend on either the physical velocity, lowercase u, or the target velocity, capital U. So if there is any one of you in the audience that is familiar with other control techniques, such as, for instance, optimal control, this is slightly different and, let's say, weaker. So this is not optimal control in the sense that we are not looking for the best control possible, where by best I mean that this square norm of the difference between the physical and the target velocity is minimized. Rather, we'll be happy anyway if we find, and typically what we will find will be a suboptimal control or a suboptimal forcing term, such that at the very least, this squared norm may not be minimal, but at the very least should decrease in time. So this somehow justifies the word control. Then this is called feedback control. So the adjective feedback is in the sense that the forcing term will typically operate by quantifying the distance between the physical velocity and the target velocity at the current time, and then react instantly accordingly. So in practice, the dependence on the physical velocity will actually be not very much on the physical velocity itself, but on the difference between lowercase u and capital U. And I promised you that I was looking for a technique that could be practical, especially when at some point in the future we'll be applying it to realistic application. Right now, these are only test cases. And in this sense, we think that this is a practical technique because it only requires adding a forcing term in an existing Navier-Stokes code, while instead, if we went for the optimal control route, this would have required, at the very least, more coding effort, in the sense that it would have required solving for an additional equation for the adjoint variable. So now that I've set up the scene of this feedback control, probably the first question that we should answer is, okay, so how should you choose this feedback control? So to answer this question, we started from an earlier work dated 2000 that you can find with reference 3 at the bottom of the slide. And in that work, the authors, Gunzburger and Manservisi, proposed to choose a specific control law, which, for the sake of these slides, I will be denoting with FA gamma, where A will be a sort of keyword for this is the first proposal, while gamma instead will represent a parameter that will appear in the definition of the control law. So I will read out loud the expression in a few seconds, but let me skim through this theorem. So this theorem says that given a parameter gamma, if you choose the control law according to this expression that I will read in a few seconds, then as long as gamma is greater than some constant m, then you're sure that there is exponential convergence of the physical velocity to the target one. That is, you are sure that you are actually able to reach the goal you were willing to do. And the exponential convergence rate is governed by the difference between the parameter gamma and this constant m, which is the lower bound for gamma. So the actual statement would have required weak solutions and would have given a few more details, but that's not relevant right now. And now, as promised, I can give you a few more insights on the actual expressions that appear in the theorem. So about the feedback control law, we realize that it's given by the combination of two terms. So the first term is a term that mimics the momentum equation of the Navier-Stokes equation, except for the fact that this sort of residual is applied to the target velocity rather than the physical velocity. The second addend instead is an addend which measures, as promised, this difference between lowercase u and capital U, and is combined to the first one by means of the coefficient gamma. So now to finish up this discussion, let me also give you an insight on how is this constant m constructed, because this will be partially the bad news of this result. So now let's go to the definition of the constant m, and in particular in this definition, let's have a look at the term which is in the square brackets. So now let's try two cases. Let's try first the case, two cases depending on the viscosity nu. Let's imagine first the case in which nu is very large. So if this nu is very large, there is an addend minus nu. And if nu is really very large, out of the two, the minus nu will dominate. So the quantity in the square bracket will be negative. And with the maximum with 0, the maximum with 0 will be 0. So this means that if nu is very large, that is for laminar flows, you are free to choose capital M is equal to 0. So you are free to choose whatever value of gamma you want. However, that is not the setting we are interested in. So we are interested in the setting which nu is very small, that is turbulent flows. And now if you look back at these square brackets, you will realize that the term in the square bracket, if nu is very small, will likely be positive. I haven't explained to you how K0 is constructed, but let's say at some point, if nu gets sufficiently small, out of the two terms, the first one will dominate. And therefore, the constant m will be strictly less than 0. So this means that we will not be able to guarantee exponential convergence for an arbitrarily small value of gamma. So what we set out to do in this preprint number 1 was to find an alternative formulation in which we do not have any constraint on gamma. So we are free to choose gamma even equal to 0 if needed, by formulating a different control law. And in particular, this different control law is slight extension of the previous one. So you see that now the new control law, I will be calling it FB of gamma, where B is the second version of this control law, which is given by the previous one, FA gamma, plus an additional term. So this additional term, as promised, is still linear in lowercase u minus capital U. And however, with just this small addition, we are able to show that there is exponential convergence for whatever value of gamma positive, and the exponential convergence rate is quantified in this case as gamma plus C0 times nu, where C0 is a constant that comes up throughout the theorem, but right now I don't want to quantify. So the good news or let's say the improvement over the previous result, is that even if nu is arbitrarily small, as in turbulent flows, the exponential convergence rate is still guaranteed, even when gamma is equal to 0, because even if in this addend, in the exponential, even if gamma were to drop out, there is still the term C0 times nu. So these two theorems are set out in the strong form, but then in principle one can repeat the same proof, or not really the same, but like similar proofs, also in a discrete setting. So for our implicit Euler plus finite element discretization. So I do not want to read out loud these two formulas right now. We have the opportunity to do so in a few slides. I just want to point out that, again, you can interpret this as exponential convergence. Just keep in mind that I am denoting with n the time step number. So this is, again, an exponential convergence with respect to the value of n. And I also want to point out that if you look at this expression in red, you will see that the same, the constants, so the base of the exponential, is still governed by the same quantities. So in the case of the first of the proposed feedback control law in the 2000, there was this sum between a term minus nu. And in our proposed control law, again, at the denominator, there is still the same quantity, gamma plus Z0 times nu. So the results that we obtained at the continuous level also descend in the discrete level as well. And now, before I continue on to the second ingredient, I would like to stop for a moment and give you a numerical test case, just to convince ourselves that this proposal is actually an improvement over the previous one. So to do this, we'll choose a target velocity capital U, which is time independent. We'll choose a viscosity which gives us a Reynolds number equal to 1000. And we'll choose two different values of gamma equal to 1 and gamma equal to 5. So the goal in comparing these two different values of gamma is because we expect that in the first proposal, in the first feedback control law, there will be not all values of gamma will work. So, and in particular, spoiler alert, the value of the constant capital M will be between 1 and 5. So one of these two values, 1 and 5, will not be giving us good result for the former proposal. While for our proposal, the goal of the picture on the bottom right will be to show you that regardless of the value of gamma, we do get this convergence. So in the picture on the bottom right, I have a plot in which on the horizontal axis, there is the time. On the vertical axis, there is the quantity that we would like to see decreasing. And so it's the distance between the finite element velocity and the target one squared in the L2 norm. And there are 4 curves, and if you take curves with the same color, the green color will mean curves which are obtained with the legacy method, the method of the 2000, while the pink curve are results related to our proposal. And each of these curves has a marker. So star marker are associated to the case gamma equal to 5, so a gamma which is, let's say, large, while square marker will be denoting the case gamma equal to 1, so let's say gamma small. And if you compare these 4 configurations, let's try the case of the star markers first. We will see that when gamma is equal to 5, both feedback control laws are indeed able to give us a curve that goes towards the horizontal axis. So since this horizontal axis is a measure of the distance of, say, the error, in other words, this means that both control laws are able to steer the physical velocity to the target one. Instead, for the case of the square markers, which corresponds to gamma equal to 1, we see that there is this curve here, which is clearly not converging. And this curve, which is badly oscillating, is the curve associated to the original feedback control law. So indeed, this is an experimental confirmation that this constant, capital M, is a value somewhere between 1 and 5. So in practice, we cannot choose for this former proposal a value of gamma which is too small, 1. While instead, if you look out in this picture for the square markers in the pink curve, you will see that instead our proposal is able to decrease the error over time. So since hopefully this is convincing enough, from the rest of the presentation, I will be only using our proposed control law. And for the second part, so now I moved to ingredient number 2, I will be discussing instead regularization technique. So now when we move the discussion to regularization technique, we will be looking at what happens when the viscosity is very small. So, and to give us an intuition and a motivation, it's helpful to have a look at the discrete convergence result that I had skipped because I promised you that I would be discussing it now, and in particular at the constant highlighted in red. So now let's try and take the limit of this constant in red when gamma goes to 0 and also when nu goes to 0. You will see that this constant in red deteriorates, so goes to 1, which means that the exponential convergence will be slower and slower. So what I was discussing before was the case in which nu is fixed. So for nu fixed, this constant will still be bounded away from 1, but as soon as you also let nu go to 0, then the combination of the two will give a convergence that deteriorates. So is this somewhat a surprise? We argue that it isn't, in the sense that it's well known that forget for a second about gamma. When nu goes to 0, the Navier-Stokes discretization itself requires some work, and this work in our setting is encoded into a stabilization or a regularization. So now the rationale for this second ingredient is the following. So I've spent the first 20 minutes in discussing that this feedback control law, this feedback control system, say, in contrast to other control formulations, is only a slight modification of the original Navier-Stokes equation. And by slight modification, I meant the addition of a forcing term. So the rationale is, since it's only a small modification, what if we try to apply regularization techniques that were originally developed for the Navier-Stokes equation to the slightly modified system? And would they work? And would they be helpful in obtaining a better convergence result? And there are several possible stabilization techniques or regularization techniques. In particular, I will be focusing on evolve, filter, relax regularization, which is divided in these 3 steps. So the first step, which is called the evolve step, requires to solve the same feedback control law as we discussed up to now. So basically, if you already have the code of the feedback control law, or let's say of a Navier-Stokes solver, this is practical in the sense that what you will need to do will only be to add 2 further steps. The second step is a filter step. So this filter step takes the velocity output of the first step, which I called U tilde, and smooths it out using a filtering radius that I called delta. So the filtering radius, delta square, is typically of the order of the mesh size. Now, the smoothed out or filtered velocity, which is denoted by U bar, now we have 2 velocities, and in the third step, which is the relaxation step, we do a convex combination of them. And the result of this convex combination will be our approximation of the physical velocity, lowercase u. So the coefficient in this convex combination, which I call with key, is typically proportional to the time step size. So this is practical in the sense that once you have the first step, the evolve, the 2 remaining steps should be easy to implement. The second step is just solving a Poisson equation. The third step is just taking a linear combination of unknowns. And those are easy and do not require to modify the already existing code for the first part. So we continued our analysis of this regularized technique, and we managed to obtain a convergence result. In this case, the convergence result, I will have to present it to you, in the discrete setting, because as you see from this slide number 12, this model is only set in the time discrete setting, because it's only after a time discretization. So basically, I will not be showing you an equivalent result for the strong formulation, only for the discrete formulation. And I have highlighted in red the differences compared to the previous result. So there are 2 main differences. Let's start from the first one. So let's start from the one in the first addend. So this first addend is again on the left-hand side of the inequality. There is again the distance between the physical velocity and the target one at time step n. This distance is related through an exponential, so there is a power n to what the distance was at the initial time. But compared to the constant that used to be at the base of the exponential, there is a new factor. This new factor, 1 over 1 minus chi, is less than 1, because chi is always greater than 0. So basically, this factor 1 over 1 minus chi is helping in obtaining a faster exponential convergence, even in the case in which gamma and nu go to 0. So this first addend is the good news. So by choosing a good value of chi, we can increase, we can have our feedback control system converging faster. However, the second addend is instead the bad news, in the sense that the bad news in this term is that if you look at this at the top of this parenthesis here, there is no exponent n. So basically, this second term here isn't going to 0 when n increases. So this will mean that there is a plateau, and we can expect that the plateau will dominate at some point, because the first addend will go to 0 exponentially fast, and at some point, only the second addend will remain. In this bad news, somehow the encouraging part is that this plateau is proportional to chi But before I told you that the parameter key is typically proportional to the time step size. So the encouraging fact is that the height of the plateau will be typically small or large as the time step size. So this motivates, looking at these two expressions, motivated us into finding an adaptive strategy, in the sense that at the very first few time instances, we look at the first term and we appreciate the first term because it gives us a faster exponential convergence. So at the first few time instances, n equal to 1, 2, etc., we definitely want to keep key greater than 0. That is, we definitely want to keep stabilization to guarantee a fast decrease of the first addend. However, at some point, we will consider that the first addend is below some tolerance, and the beneficial effect of the first addend is now negligible, let's say after a certain value of lowercase n. And after that beneficial effect has vanished, then there is no need anymore to keep key greater than 0. Because if we decide to drop key out of the formulation, then also the second addend would disappear. So in other words, for n large enough, we are willing to accept the slightly lower convergence rate of the standard feedback control law, which doesn't have this term, since the benefit of having it is outweighed by the detrimental effect of having introduced the plateau introduced by the second addend. So again, to have a pause and have a look at some numerical results, we will consider now a comparison for the same value of nu as before, but this time, so a small value of nu, and in this case, also a small value of gamma, 10 to the minus 4. And in the plot that you have on the right, you have on the horizontal axis the time, on the vertical axis the difference between the physical velocity and the target one, as before, and 3 curves. The light blue curve corresponds to the case before the introduction of the second ingredient, so key equal to 0. The orange curve corresponds to having this regularization enabled every time, and with key equal to delta t. The orange curve instead, the green curve corresponds to this adaptive strategy, which automatically switches between enabling the regularization, delta t, or disabling it, setting key equal to 0. So if we look at this picture for, let's say, time less than 2, we see that the orange line, having the regularization, is always below the blue line, which corresponds to not having the regularization. However, if we look, let's say, for time greater than 3, we see instead that the orange line reaches a plateau, while the cyan line, the line without regularization, would have kept decreasing. So our proposal, this adaptive strategy, which is this green line, is somewhat in between, in the sense that for small times, it gives an accuracy which is comparable to the orange line. For large times, it gives an accuracy which is comparable to the light blue line. And for intermediate times is somewhat in between the two settings. And now that we have concluded also that we are able to compute a regularization technique with this adaptive strategy, we can finally build on top of this previous machinery our reduced order model. And the question that I will have in these couple of slides is related also to a previous work that we have with Maria Strazzullo, Michele Girfoglio, Traian Iliescu, and Gianluigi Rozza, and is related to the fact or the questioning whether now that we are convinced that it's best to employ some form of regularization technique in the high fidelity scheme or in the full order model, the next immediate question is, do we also need to employ it for the reduced order model as well? Or maybe we can just leave without it in the reduced order model. So in this this slide and the next one, I will be comparing two cases, basically, if the answer was yes or the answer was no. So if the answer was yes, then during the online phase of the ROM, we will have the same regularization strategy. So the regularization strategy that I chose was an evolve, filter, relax, which had these 3 steps. So during the online phase of the reduced order model, we will have the same 3 steps only in the reduced order space. So the evolve step will still be solving the feedback control system. The filter step will still be solving smoothing out the resulting velocity using a Laplace filtering. And finally, the relax step will be again a convex combination of the reduced order velocity that we find. Instead, if the answer is no, we will simply drop out the filter step and the relax step and only take the evolve step. And in the context of this seminar, I think it's also important to highlight that this control term in a reduced order model can still be assembled efficiently. And because the expressions that I gave you at the beginning of the presentation are linear in the physical velocity. So that's why from the very beginning, we set out to have these expressions with that requirement, because at the end, we wanted to be sure that we could still pre-assemble even the control term in the reduced order model. So in the figure that now you have on the right, we have the comparison on the same numerical test case as before, so the same value of nu and gamma, between 2 different reduced order models, which basically correspond to the answer yes or no to the previous question. The orange line corresponds to the case the answer is yes. So we enable regularization for both the high fidelity and the reduced order model, while the green line corresponds to the no. So we enable regularization for the full order model, but not for the reduced order model. The horizontal axis shows as before the time. The vertical axis shows as before the distance between the physical velocity and the target velocity, but this time the physical velocity is the result of the reduced order model rather than the finite element scheme. And if you compare the curves in the picture, it's quite easy to see that one of the two, the case, the orange one, is always below the other one. So the orange one was the curve corresponding to the answer equal to yes. And furthermore, on top of being below the other, so on top of giving a better error, or a better, let's say, a smaller distance, it also seems to give us a more, let's say, a more regular convergence. By regular, I mean a monotonic decrease, while instead, if you look at the green line, it has a pattern which is, let's say, more irregular. And Overall, the trend of the orange line closely resembles the one that I had presented to you a few slides ago for the full order model, with a small error, with a, let's say, a small increase by, or an order of magnitude, more or less, due to the reduction of the spatial discretization with a value r equal to 20. Okay, so now let me ask how much time do I still have, just to have an idea on how quickly I want to go through this final part.
Yeah, it's almost done, but we are quite flexible. I mean, the people are free to leave.
Okay, so I
but-
will try
but-
and go. I will try and go quickly through this part. Let's say I'll try to finish by 8 p.m. My time.
All right.
So in the second part, we discuss a new approximate deconvolution regularization technique. And so in the setting of this presentation, somehow this is a continuation of the third ingredient that I presented to you before, but in a case in which the regularization technique that we use in the reduced order model is different from the one that we use at the finite element model. And in this work, we introduced a new regularized technique, which is based on an old idea. This old idea by Leray in 1934 is to come up with a regularized version of the Navier-Stokes equation in which the nonlinear term u dot grad u is replaced by u bar dot grad u, where u bar is a filtered velocity. So, and the filtered velocity, as we already have done in the first part, is obtained by solving this Laplace equation. So the new regularized model that we introduced corresponds to adding a third step on this original proposal by Leray. So the original proposal by Leray was to replace u dot grad u in the Navier-Stokes equation with u bar dot grad u, where we imagine that this u bar was the application of a filter operator g to the original velocity, to original velocity u. What we will do instead is, rather than using in the nonlinear term this velocity u bar, we will try to introduce a deconvolved velocity, which is something in between the original velocity u and the filtered velocity u bar. Why is it that we are interested in doing that? Is that it may very well happen that the filtered velocity is, let's say, very much filtered or over diffusive. So by introducing a third step, we will try to obtain an intermediate, an additional velocity, which is still a regularization of the physical one, but not as diffusive as in the original proposal. So to do this, we rely on approximate deconvolution techniques. And in particular, there are many approximate deconvolution operators. And in the context of this work, what we tried to do was to choose a specific one, which is called Lavrentiev regularization technique. But maybe for people coming from other fields, this is probably better expressed as a Tikhonov regularization, where the coefficient mu represents the parameter in this Tikhonov regularization. So overall, this gives us another reduced order model in which there are three unknowns: the physical velocity, the filtered velocity as in the original Leray model, and finally, this approximately the convolved velocity. These three unknowns need to satisfy are the solutions, again, of three equations: the Navier-Stokes equation, the filtering equation, and an additional equation which comes out of the specific approximate deconvolution technique. The good news is that in a reduced order model, even this third equation is of small dimension and uses the same operators as the other two. So again, the same stiffness matrix, the same mass matrix. So it's a third equation which is as inexpensive as the other ones and doesn't require us to pre-assemble anything new. So to compare these three possible reduced order models, we chose this backward-facing step case for a case that corresponds to a Reynolds number of around 1500, and we tried to make it as challenging as possible for the new reduced order model. And we did so with these three choices. So the first choice is a very small number of POD modes. This will typically mean that the basis is inaccurate, but is attractive because it offers large speedups of the order of 1,000. Then the second challenge that we threw at the reduced order, at our new reduced order model is to start from a value of the filtering radius very large. That is, start from a filtered velocity which is very much over diffusive. And in terms of this choice of the regularization parameter, then this was basically done by means of a trial and error. So at the bottom of the slides, you have two pictures. The picture on the left compares in the kinetic energy for three reduced order models, which are denoted with colors, and the projection of the finite element method, which is the black curve. So the red curve is the Galerkin, is the standard reduced order model. The green curve is the classical Leray reduced order model. The blue curve is our proposed reduced order model. So you see that the Galerkin reduced order model has a kinetic energy which is increasing, which is not physical. Instead, the green curve, the Leray reduced order model, has a kinetic energy which is decreasing, which is just another way of saying that this reduced order model is diffusing too much. While instead, our proposed reduced order model in blue is, while surely it's not perfect, at the very least is the one of the three that is the closest to the finite element data. And a similar conclusion can also be obtained on the image on the right by comparing the relative errors in the velocity. And for instance, if you look at the final time, you will see that the blue line is the one that achieves the smallest error. So to sum up, the goal was to introduce a flow control strategy for turbulent flows. In the first part, we introduced this feedback control law and regularization technique based on evolved filter relax. And in the second part, we introduced a novel regularization technique based on this approximate deconvolution. So I thank my co-author, and I also thank the funding agencies that sponsor this work. So thanks very much for attending, and I'm open for questions.
Thank you so much, Francesco. So we are over time, so many people already left, but let's have a Q&A session. I personally enjoyed it a lot.
Thanks.
That's awesome. All right. Okay, looks like there's a questions. Question by Joey. This was a really interesting talk. I would love to learn more. Could you share a list of references you cited? We are going to share the this actual talk in the YouTube channel, and you can actually look into those video, or maybe Francesco, you can share this slide with me, and I can.
Yeah,
accept the
sure.
Joey.
I would say that if you look at these two references, most of the references I cited throughout the presentation are contained in these two references. But yeah, I can send you the slides as well. Yes.
Awesome. I'm sure if Joey you email Francesco directly, he will be happy to directly share that with you as well. Okay, awesome. I have a not about the reduced flow model, but in the first part, so looks like the analysis, like the error bounds analysis you have done for the feedback control, you do not assume that your target velocity to be time dependent, time independent. It works, for the time dependent target velocity.
Yes. So in principle, it could. So the statement of the theorem doesn't assume time independency. It's our test case is for simplicity only consider time independent velocity. But the statement of the theorem are more general than the numerical results. Yes.
Understood. Yeah. So, but in theory, some sort of the smoothness conditions on the target velocity with respect to time, that has to be maintained, like it has to be at least continuous, or
so there are some smoothness conditions. They are part I left out. There are some smoothness conditions on the target velocity, both in space and in time. So I think we inherited most of them from the original work. So I don't think that our improvement was to change the smoothness condition compared to the original work. So our improvement was mainly focused on changing the value, on allowing for smaller values of nu.
One other question is, how does the that U0 minus U0, like on the right hand side, the difference between the initial target and the actual physical velocity, what about they are really big? You start with a really different velocity field. It doesn't matter. It's always that due to that error bounds, as long as that all the assumptions is met, then it does.
So if you look at this error bound, it will not matter.
Right.
Because it's just
by theory.
A multiplicative constant.
Right.
Maybe the one thing you have to be aware of while doing this numerically is that since this is a nonlinear problem, then you might have more difficulties in getting your nonlinear solver to converge. That may happen, but for the theory, it shouldn't matter that much.
Okay. Yeah, it's always nice in theory. Yeah. All right. Sounds good. In application wise, if you can give us, some interesting application where this feedback control might be useful.
Yeah. So this is part of let's say a bigger work that where the final goal would be to apply this to, let's say, turbulent control, like for applications in I don't know if like aerospace industry or something close to that. Of course, we are still a long way. It's still far away. At least now we are more in setting out the methodology. The next step would be to try to go towards more challenging cases like turbulent flows at higher Reynolds number, but maybe in, let's say, still simple three-dimensional domains.
Okay, awesome. All right. I have one more questions, but let me save it for later. Okay. Is there any other questions? I think only a few of us left. Only two of us left. Well, thank you so much, Francesco,
You're
for the
welcome.
nice talk, and I enjoyed it a lot. And with that, let me just stop the recording.
Great. Thank you. Bye.